On Earth, solar power fights a constant battle against the planet itself. The atmosphere scatters photons, weather systems block them entirely, and for half of every day, the sun simply disappears. But if we move exactly 36,000 kilometers above the equator, we reach geostationary Earth orbit. Out here, there is no weather and no night. Satellites parked in this orbit experience a raw, unfiltered solar barrage nearly 24 hours a day. Historically, capturing that energy required massive, rigid infrastructure. The arrays powering the International Space Station are heavy and complex, relying on large mechanical joints to keep the panels pointed at the sun. Modern orbital architecture discards those heavy mechanics. Current designs use ultra-lightweight, modular arrays that can unfold in the vacuum of space, generating direct current locally with zero moving parts. Harvesting the solar energy is no longer the primary engineering hurdle. The real physics challenge is figuring out how to transport gigawatts of that captured power 36,000 kilometers back down to Earth without a single wire. To send power across the void, we use microwaves, but a raw microwave beam in space hits an immediate physical barrier: free space path loss. Following the inverse square law, an unfocused wave naturally spreads outward, weakening exponentially as it travels. We can calculate this decay using the free space path loss equation. Because the distance variable d is a staggering 36,000 kilometers, the math shows that the vast majority of our power would dissipate before it ever reached the atmosphere. Without a mechanism to perfectly steer and concentrate that microwave energy, the harvested solar power would simply scatter into deep space, long before reaching the grid. The solution is an electronic steering mechanism called phased array beamforming. Instead of moving a heavy dish, we use a flat array of tiny antennas. By staggering the timing of each pulse by a fraction of a nanosecond, we can manipulate how the waves interact. Imagine a wave pool where multiple pebbles are dropped at perfectly timed intervals. In most directions, the ripples cancel each other out through destructive interference. But in one specific path, the peaks align and reinforce each other, forming a single, massive wavefront that carries the concentrated energy of the entire array. To lock that beam onto a ground station, the satellite uses a retrodirective pilot beam. A low-power uplink signal is sent from Earth, acting as an unshakable target for the satellite to track. When the satellite receives that pilot signal, it mathematically inverses the phase of the wave, a process called phase conjugation. This guarantees the high-power microwave downlink exactly retraces the path of the pilot signal back to the receiver. This closed-loop control provides an ultimate fail-safe. If the satellite structurally deforms or the pilot signal drops, the math breaks down, and the power beam instantly and harmlessly defocuses into the void. Once the beam reaches the surface, we face one final conversion. Standard electrical grids cannot absorb raw 5.8 GHz radio frequency microwaves. To catch it, we use a rectenna, a rectifying antenna grid. The critical microscopic component doing the work here is the Schottky barrier diode. Unlike a standard PN junction diode, a Schottky diode uses a direct metal-to-semiconductor contact. This architecture bypasses the slow switching speeds of standard electronics, allowing it to efficiently convert high-frequency microwaves back into the direct current used by our grid. Mastering this semiconductor interaction completes the conversion chain, allowing an invisible orbital circuit to connect the harsh vacuum of space to the terrestrial grid. For decades, the primary barrier wasn't the physics of the beam, it was the cost of the launch. Lifting millions of kilograms of solar hardware into orbit using expendable rockets was simply too expensive to justify. But the emergence of fully reusable, heavy-lift space transportation is shifting the math. Launch costs are dropping from $20,000 per kilogram toward a critical tipping point of under $500, making large-scale orbital construction a practical possibility. With the launch barrier easing, we are approaching a window where wireless orbital power becomes a viable pathway for the global grid. These systems could beam gigawatts of clean baseload power directly into disaster zones, into remote communities, or human outposts on Mars. The solar energy in our orbit is constant and practically limitless. We now have the mechanics to catch it and the physics to bring it down. To follow the transition from terrestrial grids to dynamic orbital networks, subscribe to Sci-Tech and join the learning quest.